Let us now present another proof of the famous theorem of Nash. So that proof is very, in my opinion, very intuitive, very beautiful, and that proof was given by Ron Holtzman at a lecture at the Technion Israel Institute of Technology. That proof is based on the theorem of Brouwer, which is another fixed point theorem, and that theorem very famous and very useful, in particular for the proof of equilibria, of the existence of equilibria. That theorem in our case is given as follows. So let S be a non-empty subset of the Euclidean space, which is convex, closed, and bounded. Since in the Euclidean space being bounded and closed is equivalent to being compact, we can say that let S be a non-empty convex and compact subset of the Euclidean space of a finite dimensional Euclidean space. Assume that F is a function from S to itself, which is also continuous, then F has a fixed point, which means that there exists X, a point X in S, such that F of X is equal to itself, to X. And the intuition of this proof is to express the notion of Nash equilibrium such that it would be exactly the same as a fixed point of such a function, and then Brouwer will imply the existence of Nash equilibrium. That's highly non-trivial to express this, and so that's not immediate, but that's the intuition. So the proof goes as follows. From the fact that we assume the game is finite, we can just write the strategies, the set of pure strategies of each player as a list in any order. We just fix an arbitrary order. So Si is Si1 till Si Mi. Mi is the number of strategies in Si. And then a general element of delta Si of the set of the mixed strategies of player I is the set of the probabilities of the numbers Pi1 till Pimi, where each number gives the probability of the corresponding pure strategy. These numbers are all non-negative and their sum is 1. Now, let us then define M to be the sum of Mi's. So Mi is what denotes the number of strategies of player I. And let us denote by M the total number of all the strategies of all players. And then the vector P of all the mixed strategies of all the players. So the vector P, which is a profile of mixed strategies, is going to be a vector in Rm. Now, we know that each capital delta of Si, so each set of the strategies of player I, of the mixed strategies of player I, is convex, closed, bounded, and non-empty. So I won't prove this to the last detail, but basically the strategies of player I are all Pij's, such that they are non-negative and their sum is 1, which means that which means that is convex. It also means that the fact that we have the equality, it means that it's closed. Of course, the sum is 1, so it's bounded. And it's also non-empty because, for example, when some Pij is 1, the others are 0, that's an example of an element in this set. So that is an example of an element in delta Si, and therefore their Cartesian product the finite product of delta S1 till delta Sn, is also convex, closed, bounded, and non-empty. Now, let us start with this transformation from the problem of mixed equilibria to the problem which can be handled in Brouwer's theorem. So for any strategy profile in delta S, for any player and for any number of these player strategies between 1 and mi, let us P kind of restricted to S, not restricted, but P, let's call it with the deviation Sij, denote the strategy profile when player I deviates from the pure strategy to the pure strategy Sij from the pure strategy which it originally played under Pi. So Pi means that player I plays this strategy. That's not necessarily a pure strategy, that's some mixed strategy. So let P deviating to Sij denoted like that with a vertical line. So a vertical line Sij denote the strategy profile when all the players play exactly as they play according to the strategy profile P, while player I deviate to the pure strategy Sij instead of playing Pi. Now let us somehow measure what the player gets from her deviation, her unilateral deviation. So let us define the following function for each player and for each strategy of that player. So player I strategy j. And the function is gij takes the vector, the strategy profile P, and it's a maximum of what the player gets from deviating and 0. So we look at the utility of player I in the mixed extension from changing from Pi to Sij minus the utility that the player originally had in her original profile Pi. So the utility that player I gets from deviating from Pi to the pure strategy Sij, formally player plays a mixed strategy which gives probability 1 to Sij and probability 0 to everyone else. So if the player gains something, then this is just what we write here. Otherwise, we define Gij as 0. So Gij is either what the player gains, and if it's something which is non-positive, if the player loses from this deviation, then it's just 0. And then we observe the following facts. So first, player profile P is a mixed Nash equilibrium if and only if for each player and for each strategy of that player, for each number of the strategy J, Gij on this P is 0. Because being a mixed Nash equilibrium means that no deviation can help. And that's exactly what it means, that Gij is 0 for every I and j. Now the other direction, that if we know that Jij is 0, that means that no deviation to a pure strategy can help. But since we define the mixed extension linearly, and capital Ui is the expectation, therefore, if no deviation from a pure strategy can help, then also no deviation can help at all. So, indeed, being a mixed Nash equilibrium is equivalent to all those Gijs having their 0 point in P. Then another fact is that all the GIJs as functions, they are continuous, because we just take P, we change it to, we change one of the strategies. So we say that instead of PI, we go to the strategy that plays deterministically Sij. Then we have those UIs, which are linear, and then we have a maximum. So these are all continuous. All continuous in P. Okay. So we have seen that that the set of all the strategy profiles of the mixed extension is convex, closed, bounded, and non-empty. And we have defined GIJs, which define basically they express what the player gains from deviating to the J's pure strategy instead of what the player does at point P. Now, let us go further with this translation from the game to this function from a convex, compact, and so on set to itself, which we can then handle with Brouwer. And let us define for each player and for each J, for each number of strategy of a pure strategy of that player, let us define Fij as Pij plus Gij. So intuitively speak, well, let me just say it. Pij plus Gij normalized or formally divided by 1 plus the sum of Gik, k going from 1 to mi. So we intuitively speaking, we want to have a function from the set of all the mixed strategy profiles to itself. Now, such that Nash equilibrium will be equivalent to a fixed point. Now, we have said that a Nash equilibrium is equivalent to the function Gij having zeros. Therefore, a Nash equilibrium is equivalent to the function that Gij plus Pij is staying as it is. So P is a Nash equilibrium if and only if those functions, just because Gij will be 0, and then Gij will plus Pij will just give us Pij. Yes. So the nominator helps us to basically translate an equilibrium, I'm just speaking intuitively now, to a fixed point. No, not really. It's going to be too large. The function is not going to go to the set itself. We need to normalize it. And therefore we divide it by what we divided by 1 plus the sum of all the GIKs. So GI of all strategies case of play I, to normalize it. And that's going to give us the ij's coordinate of the function we need. And okay, that was the intuition. And let us now go over the formal properties of this Fij. So we have the following. First of all, the sum of Fij when j goes from y to mi is okay. So just for the same I, the denominator is the same, and so we just need to sum in the denominator, and the sum of Pij's will be 1, and therefore we will get 1 plus the sum of Jj's divided by the same, and therefore we will get 1. So the normalization works, the sum of all those functions is 1. Now, since all the GIJs, by definition, they are non-negative, the sum of excuse me, Fij is also non-negative. And the last part is that Gij's are continuous. Now Pij relatively to the vector P is the projection on some direction, and therefore Fij is also continuous. So having established those facts that for each I, the sum, when you go over all the j's from 1 to the number of strategies of play I is 1. For each I and j, Fij is non-negative, and for each I and j, Fij is continuous. Let us finally get to see how we can make the last step of moving from the problem of a Nash equilibrium to the problem which is basically solved by Brouwer's theorem. So we have seen that the sum of Fij's when j goes from 1 to the number of strategies of play I is 1, and for each I and j between 1 and mi, Fij is a non-negative function. That means that if we look at the vector transformation from the m vector p to the vector fi1 of p, f, and so on, fi2 of p, fi till fimi, and excuse me, f11 of p, f12 of p till f1m1, then f21 of p, f22 till f2m2, then f3 and so on, then finally fn1 till fnmn. Then it's going to be a transformation from the delta of s to delta of s, because we know that all those components are non-negative and their sum is 1. Exactly what delta of s is. Excuse me, not the sum of all the components of capital F is 1, but for each I, the sum of all Fij's when j goes from 1 to mi is 1. That's exactly what means that the parts which result from fi something is in the set of mixed strategies of player I, and therefore all the vector sits in the Cartesian product of delta s i's of mixed strategies of all the players. Therefore all the product sits in the delta of s. So this is a transformation from the set of mixed strategies, the set of mixed strategy profile to the set of mixed strategy profile, delta of s. Now we also said that for each I and for each j, Fij is continuous, and therefore also f, a finite combination, is continuous. Here it's important, by the way, that it's finite. And so we have made a transformation from the set of mixed strategy profiles to itself, which is continuous. And remember what we know about the mixed strategy profile. It's not empty, it's convex, it's compact. Therefore, Brouwer's theorem implies that there exists a fixed point in this set of mixed strategy profiles with respect to this f. That's not all. So there is a p, a vector p, in the set of mixed strategy profile. So there is a mixed strategy profile p, such that the capital F of p is equal to p. It means for each player, and here it's a typo, for each j, let me change it. That for each player I, and for each strategy number j between 1 and mi, the Fij of P is exactly Pij. So that's a component of this transformation, and P is a fixed point. Good. That, by definition of F, remember F, how F is defined. That means that the fraction Pij plus Gij of P divided by 1 plus the sum of Jk's of P, that's Fij, equal to Pij. Now simple multiplication by the denominator 1 plus the sum of Jk's of P says that that is exactly the same as this. Then Pij's get cancelled, and we are left with Jij is equal to Pij times the sum of Gj's. Okay. It's if and only if, but what we need is actually that having this fixed point, we have implied that Gij is equal to Pij times the sum of Jk's of P. Okay, next. We're almost there. We have proved that there exists a P in the set of the mixed profiles, mixed strategy profiles, delta S, such that Gij of P is equal to Pij times the sum k goes from 1 to mi of Jk's of P. Now, we have already said that P is a mixed Nash equilibrium, a profile of mixed strategies is a mixed Nash equilibrium, if and only if for each plan, for each strategy J, Gij of P is 0, because Gij measures what the player gets from a deviation. And we said that this matches all the pure deviations to pure strategies, which is basically enough because it's linear. So we need to basically prove that for this P, we have that for each plan for each J, Jij is of P is 0. Assume to the contrary, that's not the case. Assume that there exists an I and there exists a J such that Jij of P is strictly positive. Since Jij is never negative, the contrary to being 0 is being strictly positive. Now from this, we can immediately imply that the sum of those is definitely strictly positive because they are non-negative, and at least one is strictly positive. So since the sum of Jk's is strictly positive, and remember what we have proved here in the frame that the sum times Pij is equal to Gij. It means that for each J prime, if Pij is positive, then since it's multiplied by something positive, Gij prime will be positive. Let us decipher what this means, game theoretically. Now we are, as you probably see, we are going back from the result of Brouwer to game theory. So this means that for any deviation to a pure strategy in the support of Pi, I will strictly benefit. So that if Pij prime is strictly positive, So it means that if the strategy Sj prime is in the support, then the deviation to this strategy will strictly benefit the player, because that's what Gij prime measures. But it cannot be that you can get more weight to any, you can deviate to any of your currently played strategies and strictly benefit, because what you get is an average of what you play in your support. Since the average cannot exceed all the elements, weighted average, but it's still an average, it cannot exceed all the elements, this cannot happen. From this contradiction, we see that our assumption that there exists ij such that jjp is positive, that assumption cannot hold. So, in other words, for every I and j, jj of p is 0. And as we already said, since jj of p measures the gain from deviation, this is the same as saying that p is a mixed Nash equilibrium. So we have seen that the p, which existence is proven by, is guaranteed by Brouwer's theorem, is indeed a mixed Nash equilibrium, and we have proved the theorem. Please notice that here, well, if you compare the proof to the previous proof, we don't use so much kind of bombastic notions like this set is continuous or semi-convex. I even don't remember the exact word. But we don't use even the complicated, in a way, theorem by Kakutani. So we use only, shall I say, simpler topological facts, but we also have to work technically a bit more. But anyway, that's a nice proof. And please notice that both Kakutani and Brouwer are non-constructive. So none of those theorems gives us an algorithm to find such an equilibrium, such a point, a fixed point, which in this case is provided, is guaranteed to be an equilibrium. So please notice that we have proven existence, but we have not given an algorithm, at least in the general case, how to find such an equilibrium.